Hello and welcome. We're going to do lab number 2 we're going to do lab number 6, investigation number 2. And in investigation number 2, the question is simply put, what is gravity? All right, here's our issue. In all of our previous labs, all the accelerations we had were due to a visible force, a contact force between the string and the cart, or between the fan and the air. All of our forces that we've run into so far have been contact forces, and all of our accelerations we can tie directly to some sort of contact force. But in the experiment we did in investigation 1, the ball was in contact with nothing, and yet it accelerated. Okay, the ball was in contact with nothing, and yet it accelerated. And so what we can say then is, looking at, let's take a look, F equals ma. Okay, so if we write F equals ma, well, we know what the acceleration was because the object, when we let the softball go, it had an acceleration. And we know that the softball has to have mass just by the definition of mass. The question is, what is the force? What is the force that causes the acceleration of the softball as it falls? So let me switch on over. Let's take a quick view here, and I'm going to do a little experiment here. Let's start off with, let's say we have this. It says in activity 2-1, we need to use the balance or an electronic scale to determine the mass of a rubber ball in kilograms. Now, I'm not going to use a rubber ball because I'm going to use a landing pad for the experiment. And the mass we're going to use to simulate the rubber ball is this steel weight. And it happens to be, I've got it marked, it's marked on top of it, 500 grams. I'll place the mass on to the scale, and you can see the scale reads 499.6 grams. So for our purposes, this mass is to 3 significant figures, 500 grams. I'm going to jot that down on the whiteboard here. So it's 0.500 kilograms. Okay. By the way, I happen to have a wooden ball here. I'm going to go ahead and find the mass of the wooden ball that's going to come into play later on. And the mass of the wooden ball turns out to be 19 grams. I'm going to jot that down on the whiteboard as well. So it's 0.019 kilograms. All right, we'll update that as we go along in our investigation. So question 2-1. Suppose that the ball, either one of these balls, is floating in outer space away from the gravity of the Earth. Let's say the steel mass, this steel mass right here, it's floating out in space. It's outside of the influence of any planets or anything like that. It's out in the middle of nowhere. Okay? The question becomes, what is the force in newtons you would have to apply to the ball so it would move with an acceleration of a magnitude that we had just observed in activity 1-1, which is as the ball fell toward the Earth. So what I'm looking at then is I have a steel ball located here, and it's going to have an acceleration, that acceleration which I'm going to call A. And let's just say that I have to push it with something. So there's a little box, and the box is going to apply something here. So that box is pushing against the ball. What is the magnitude of the force to provide the acceleration? So I need a force in this direction, which I will call F. What is the magnitude of that force? Well, we have F equals ma that we see from our Newton's second law. So the mass of this object is equal to 0.500 kilograms. The acceleration of the object, we're going to go ahead and use the free fall acceleration of 9.80 meters per second squared. So therefore, what should the force be? Well, the force should be the product of the mass times the acceleration. So when I do the multiplication, I come up with a force of 4.90 newtons. So you can do the calculation yourself, but it's really easy. Half a kilogram multiplied by 9.8 meters per second squared gives us 4.90 newtons. Okay, so that's the force I've got to apply to get an object to accelerate with that much, excuse me. That's how much I've got to apply in order to get it to accelerate with that much acceleration. All right, now let's move on. Question 2-2, what would be the direction of the force? Well, again, according to Newton's second law, since the force is proportional to the acceleration, the force has to have the same sign as the acceleration. Since the acceleration is to the right in my diagram, the force has to be to the right as well. So the force is, the push or pull is providing an acceleration in that direction. Now we get to question 2-3. If Newton's second law is to be used in the situation where you drop the ball in the laboratory on Earth with no visible applied force, what force do you need to invent? So here's our problem. Here's our ball. It's located here. We're going to let the ball go, and the ball is going to have an acceleration downward of some unknown acceleration. Now, in the previous problem, we have an object making contact with the ball to get it to accelerate through space. But in what we saw today, what we saw in investigation 1, was there is no ball, there's nothing in contact with the ball, and so it had to, and it accelerated. For us to get an acceleration, we must have a force. And so that force is going to be in the downward direction because net force is inversely proportional to the acceleration. I got a little issue here. Hold on. There we go. So our force has to be in the downward direction, whether it's a push or a pull. So there's our force in the downward direction, providing the acceleration. Okay. So in order for Newton's second law to be valid, I've got to have this force at a distance pulling the ball. Okay? So let me sum it up. Let me wrap it up. When it's out in space, in order to get that acceleration, you have to push the ball with a certain amount of force to get the acceleration. Here on the surface of the Earth, we put the ball out in space. It's not in contact with anything, and yet it accelerates. So for it to accelerate, there must be a force pulling it down. And that force we're going to call gravity. We're inventing that there must be a force at a distance called gravity. Okay? The magnitude of this force is, well, we know what the acceleration was, and we know what the weight of the object is, so the magnitude of the force is going to be 9.8 newtons. And the direction of the force is in the direction of the acceleration. Now, so far, we've studied the motion of just one object under the influence of the gravitational force. So you should have observed that the acceleration of the falling body was constant, which it was as it fell. Is the gravitational force constant then? How does the mass of the falling object affect its acceleration? Is the gravitational force constant independent of the mass of the falling object? Just the way a horizontal push or pull with your hand on the cart might be constant. So here's where we get into activity 2-2. Prediction 2-1 is if you were to drop a massive steel ball and a not very massive rubber ball at the same time, would they fall with the same acceleration? Explain the reasons for your prediction. So there's 3 possible outcomes. And in this case, what we're going to do is we're going to accelerate either we're going to drop this steel weight and we're going to drop this wooden ball. There's 3 possible outcomes. Either the steel ball will accelerate at a greater rate than the wooden ball, so hit the table first. The wooden ball will accelerate at a greater rate than the steel ball, so it will hit the table first. Or both balls will accelerate at the same rate and they'll hit the table at the same time. I'm going to go ahead and reset and we will see how the experiment comes out. Okay, so prediction 2-1. If you drop a massive steel ball, in this case this weight here, and a not so massive wooden ball, how are they going to land? I've already talked about the possible options, so let's go ahead and do the experiment. Step number 1 is to release the two objects from the same height at the same time and observe what happens when they hit the ground. So I'll start off at about this height and let it go. Well, that's not a surprise. But what if I raise higher up, say about shoulder length? Still hits the same time. Now let's go way up here. Let me adjust the camera a little bit so we can actually see. There we go. Okay, so we'll go up to about this height, and they hit the ground at the same, hit the table at the same time. So what we see is the steel weight and the wooden ball hit the table at the same time. Again, we can compare what happens if I take this wooden weight and compare it to this coffee filter. If I drop them both from the same height, the coffee filter hits the ground much less, much quicker. Okay, so question 2-4. Did one object take significantly longer than the other to reach the table, or did they both hit at the same time? And then question 2-6. What do you conclude about the acceleration of the two objects? Is one significantly larger, or are they both about the same in magnitude? Okay. Now, what we need to do next is we need to measure the masses of the two objects, and I've already done that. As you can see, I don't know if you, let me step out of the way here. And up on the whiteboard, I've got written that the mass of the wooden object was 0.19 grams. Looks like we got a little bit of a reflection. Let me see what happens if I turn off the center bank of lights. Camera should still be able to see. Yep, it's a little better, a little easier to see. There's still some reflection, and the reflection is due to me standing in front of the computer. So what we see here is the mass is 0.0019, or 0.019. For the steel ball, what I'm going to do is I'm going to use this 50-gram mass holder in order to hold it up, and you'll see why in a moment. And so that's going to change the mass of my steel holder from 500 to 0.50, so 550 grams, or 0.055 kilograms. All right, so that's our measurement. Now, although you've only made casual qualitative observations of the two objects falling, it turns out that in the absence of other forces, such as air resistance, all objects will fall with the same acceleration. We've already quantified the acceleration. We saw that it was the same when I tossed the ball up and down, or when I dropped the ball right away. We also saw that both of these objects had the same acceleration when I let them go. We're going to go ahead and call that acceleration 9.8 meters per second squared, the free fall acceleration. From our previous calculations, we saw that we have to take that acceleration multiplied by the mass in order to figure out what the weight of the object is. So, this is where I'd break out the handy-dandy calculator. Let's calculate what those weights are supposed to be. So if we take the first one, the wooden ball, we're going to take 0.019 and multiply that by 9.8, and we end up getting a weight in newtons of 0.19, weight in newtons of 0.186. For the steel, we take 0.55, multiply that by 9.8, and that gives us a weight of 5.39 newtons. So now comes the next test, question 2-6. If you have to detect, and if you have, let me try it again, excuse me. If you have any object of mass m accelerating at a constant rate given by g, what is the equation that you should use to determine the gravitational force? The gravitational force is often referred to as weight. Well, as I said before, if you take the free fall acceleration and multiply that by the mass, that gets you the weight. Now we get to measure. And for that, I need to use a force sensor. So I'm going to reset the display here a bit. I'm going to add a digital measurement, and I need to add the force sensor. Yep, I've got a force sensor already set, so I'll just select force, and I will change the mode to keep mode. Actually, I'm not going to use the force sensor. Here's what I'm going to do. I'm not going to use that display. I'm going to go ahead and use a graph. And I will measure the force. And I will change it from keep to continuous. So here we'll start off with the force. We will zero the force sensor. And I'll go ahead and hook the force sensor onto the steel ball and let it hang, and then start recording for about a second. 1001, 1002. Okay, so we're going to hold that there. Let's go ahead and zoom in, and we see that the force downward, if I use the there we go. If I use the force downward is negative 0.21. So our force downward is 0.21 newtons. Not too bad, not as good as I want. So let me go ahead and repeat the experiment. I'm just going to zero the sensor again, put the weight on it, and then start recording for a couple seconds. And stop recording. Ah, there we go. We get a much better one. 0.186. Take a look at that number, 0.186. That exactly matches the weight that I had predicted. Now let's try the other weight. Zero the force sensor, hook the mass holder on, and let it hang. And I'll start recording. And stop recording. And I come up with a force of 0.40. Excuse me, not 0.40. You can read it. It's 5.40. So in our comparison, the weight that we measure for the wooden ball, 0.186. The weight that we measure for the steel ball, 5.40. Those are the direct measurements. What did we predict? We predicted that if we took the mass and multiplied it by the free fall acceleration, we would have a weight or a downward pull by gravity of 0.186 newtons for the wooden ball and 5.39 newtons for the steel ball. A very, very, very close agreement. You can go ahead and read the comments on page 140, but let me ask the questions on activity 2-3. Question 2-7. If mass is a measure of the amount of stuff an object has, is an astronaut's mass different on the moon? Well, let's think about it. Here's an astronaut here on Earth, has a mass of, say, 75 kilograms. Astronaut goes to the moon. Still is going to have a mass of 75 kilograms because mass is a measure of how much stuff that object has. This 500 gram weight, this 500 gram mass, is 500 grams of stuff, 500 grams of steel. If I take it up to the moon, I will still have 500 grams of steel. What about question 2-8? How can astronauts jump so high on the moon? Is the astronaut's weight different on the moon than it is on the Earth? And explain. Well, let me bring up a whiteboard, and we can explain it this way. Okay, first off, let's go ahead and do my calculation real quick. Let's say my astronaut has a mass of, say, let's call it 100 kilograms. All right. So if my astronaut has a mass of 100 kilograms, then the weight on the Earth, which would be, I'll call F sub g, his weight on the Earth is going to be 980 newtons. No, I'm sorry. Yeah, that's right. 100 kilograms is about 1,000 newtons. of weight. Okay? Now, on the moon, the free fall acceleration is 1/6. It's 1.7 times, so is 1.7 meters per second squared. So his weight on the moon, F sub g on the moon, is going to be, instead of 980, it's going to be 160 or 170 newtons. So on the Earth, he has a weight of 980 newtons. On the moon, he has a weight of 170 newtons. Okay, so if he's standing here on a planet, okay, there he is on a surface. He's going to exert a downward force, and that downward force is going to be, he's not going to exert a downward force. He has a downward force pulling him down. That's his weight, which we'll call F sub g. In order to jump, he's going to push down onto the surface. So the surface is going to push back up on him. And so it's going to be an upward force, which we will call F sub n, a normal force. Let us say that the normal force that he exerts is, call it 1,400 newtons. Okay, 1,400 newtons of force pushing downward. Okay? Now, in the case on Earth, that means the difference is going to be around 400 newtons. So let's just call it 400 newtons just to make the math the same. So he's going to have an upward force of 400 newtons, which is going to accelerate him, 400 divided by the 100 kilogram mass. So it will accelerate him at 4 meters per second squared. But what about on the moon? On the moon, you can exert the same amount of force because that's how strong the legs are. But now that 1,400 newtons of force downward is now subtracted by 170 newtons, not by 1,000 newtons. So he's going to have an upward push. Going to have an upward push of 1,200 newtons. This is just rounding the numbers. So there's an upward net force of 1,200 newtons, and if we divide that by his 100 kilograms, he's going to have an acceleration of 12 meters per second squared. That means in the initial push, he's going to once he jumps off of the surface, he's going to have a certain initial velocity coming off of the surface on the Earth, but he's going to have a much faster initial velocity coming off the surface on the moon. So, our question, 2-8, how can astronauts jump so high on the moon? It's because while they exert the same amount of force to jump, they have less weight to overcome, so the net force is bigger. Question 2-9, if weight is a force, what is pushing or pulling on the object? Well, as we see in the ball hanging in midair, the only thing that could be pulling the object downward is going to be the planet Earth. And how is weight related to the acceleration due to gravity? Well, that's a fairly simple equation. All we've got to do is take a look at our equation, F equals ma. So that means the force due to gravity divided by the acceleration due to gravity is going to be equal to the mass. This is very important. What that means is, as you increase the mass, the force is going to go up because, well, you see that the acceleration does not change. In other words, we can write another ratio that says the force of gravity divided by the mass of the object is going to give us the free fall acceleration. So if the weight goes up, the mass goes up. If the mass goes up, the weight goes up, but the acceleration remains the same. So it does not matter. It doesn't matter if an object is big, doesn't matter if an object is small. All objects will fall at the same rate. Will accelerate at the same rate. And then the last question is, when do astronauts experience weightlessness? Do they ever experience masslessness? Well, the second question is easier to answer because it is impossible for an object not to have mass. If you have mass, if you're made up of stuff, you're going to have mass. But the next question is it possible for an object to not have weight? Well, now we're going to have to take a look at things a little bit different. Okay? Is it possible for an object to not have weight? Well, let's try. If we're here on the surface of the Earth, so there you are on the surface of the Earth standing there, you have two forces acting on you. You have the force of the normal force pushing upward, and you have the weight pulling downward. Now, if those two forces are equal to each other, the acceleration is zero. You feel like you're being supported by the ground. Okay? But what happens if you aren't supported? If you are not supported, there you are standing there. Okay, there you are standing there, but you have only weight pulling you downward. There is no normal force. So therefore, you have a net force pulling you downward. So you have this feeling of falling. Do you have an absence of weight? No. You have an absence of support. That would be the same thing as if you were inside an elevator and the elevator is in free fall as well. The floor of the elevator is not pushing up against your feet because both you and the elevator are falling at the same rate. So we can have a state of apparent weightlessness. A better phrase is free fall. You're in a state of free fall. Okay? Can you be massless? You cannot. All right. I do not have the apparatus to do investigation number 3, where we do a little examination of the normal forces. So let me do a quick little discussion on normal forces, and then we can call it a day. Here's essentially how a normal force works. Okay. Let's imagine, if you will, that we have a trampoline. Right. So if you have a trampoline, it's nice and flat. But what happens if you put an object in the trampoline? Then it's going to depress and come back up. Now, why doesn't the object fall? Why doesn't the object go down to the floor? The answer is because so even though we have the weight of the object pulling downward, the trampoline is pushing back upward. If we look at the trampoline itself, if we look at it from the top, like so, there's the object in the middle, what's happening is the trampoline is being stretched out. This piece is being pulled this way, this side is being pulled this way, but what's holding it together is the molecular bonds, if you will. Okay? If you're looking at the trampoline, you're looking at the fibers, how well the fibers are tied together, or whatever the case may be. The harder you push, the more you're going to stretch on those fibers. The greater the stress on those fibers is going to be. But as long as those fibers don't break, you're eventually going to get a support force which will counter your weight. Okay? So if you push down harder, the support force has to be harder. But that also puts more stress on the bonds. Eventually, it's going to break. In that case, you no longer have a normal force, it falls apart. So to answer some quick questions, what mechanism do you think might explain the ability of surfaces to react to an active force by applying a normal force? An active force is a force that is applied actively. For example, a car running into a tree is an active force, or a book being pulled down by gravity is an active force. The normal force, the support force, is a passive force. It depends upon what the force is applied to it. That is to say, if I put a book on a table, then the normal force is going to be equal to the weight of the book. If I put an additional book on the table, that's going to increase the weight pulling downward. The normal force has to increase to counter that if there is no acceleration. If the table breaks, then there's no longer a normal force and it falls all the way through. So, again, what's the nature of the normal force? The nature of the normal force is those little molecular bonds all tied together, holding the table together, and if you put a big enough force on an object, then those bonds stretch out, and eventually, if they stretch out enough, they will break. Okay? So, that's my little discussion on normal forces. This finishes up lab number 6. My apologies for the last one. If you tried to get onto it and you saw that it had no sound, hopefully these two videos will come up and they'll post well. And if you have any questions again, you know how to get a hold of me. So take care, enjoy yourselves, and I'll see you in class.